So in some sense, what we've done so far this semester is we've basically built ourselves up to where we can do the full Newton's second law problem for an object in static equilibrium. And so the first question becomes, okay, when is an object in static equilibrium? And basically there's two conditions that need to be met. The first is it needs to be in translational equilibrium. Translational equilibrium tells us that all the forces are in balance. Second condition is rotational equilibrium. So that tells us that all the torques cancel out. So our two conditions for equilibrium are that the vector sum of all the forces have got to equal 0 and the vector sum of all the torques have got to equal 0. For us, given the fact that largely we're going to work problems in which we can draw the forces acting in the x and y direction and then think about torques that are trying to make the object rotate either clockwise or counterclockwise, so therefore think about torques that are oriented in the z direction, we're basically going to set up three equations. We're going to set up a sum of the forces in x equals 0 equation, a sum of the forces in y equals 0 equation, and the sum of the torques in z equals 0 equation. So how do we work this problem? Well, again, a lot of this at this point is going to sound really, really familiar. So we're going to start by drawing the extended free body diagram. Oftentimes that'll be just basically the picture that comes with it, and then we're going to draw where the forces act, because we need to know where the forces act when we're dealing with our torque equation. We're going to pick a coordinate system including a pivot. So the one sort of addition here is that we will very often, because there's not any acceleration, we'll be able to basically always pick positive x to the right, positive y points up, positive z will point out of the board, and then what it's really going to come down to is picking a pivot. And so we'll talk in class about sort of different choices to make about picking a pivot to make your life easier in terms of the math. For 3, and we're going to break the forces up into x and y components. And we're going to do that so we can set up our first two equations. So all the x components of our forces have to add up to be 0. That's equation number 1. All the y components of our forces have to add up to be 0. That's equation number 2. Then we need to calculate the magnitude and direction of the torque about the pivot that we picked for each force that acts on the object. So again, this is just like we've spent the last week basically working net torque problems. Well, this is just a net torque problem where here we know that all the torques are going to add up to be 0. And so we'll go through our process of calculating the magnitude and direction of the torque that each force is causing. And so we'll set up our sum of the torques equation using that information. Basically at that point we've got 3 equations, we've got 3 unknowns, and then we'll just go solve. So hopefully when we start to work this static equilibrium problems in class tomorrow, hopefully this is going to feel like a very familiar process. Breaking forces up into x, breaking forces up into y components, and then calculating the torques that are acting in the z direction. We're going to do that for each of our forces and set up our 3 equations to then go solve for our own.